So, speaking about discrete flows of Goncharov-Kenian integrable systems. Yes.
Thank you very much for inviting me for the conference. And it's, well, I really do not know if I deserve this invitation because, well, these last 4 months were not the best from the point of view of doing math. And, well, and also there is some misunderstanding about two conferences at the same time. So I decided to speak about a subject which is not really very fresh, and but on the other hand, it seems to me it fits. First of all, it's not published, so maybe not everybody knows about it, so it's very elementary. And second, it is well, it seems to me it fits to the subject of a conference because, well, discrete flows, these discrete flows, they are not, well, they are not directly Penlevé, but as we learned from some number of participants of this conference, that the Penlevé is just the determinization of these flows. So just some, well, I decided that to speak kind of what I know about the discrete flows. So this is a my main subject of the talk. And I will begin with well, just a small recall about what is the Goncharov-Kenian integrable system. So the Goncharov-Kenian integrable systems. Well, I'll make some, well, not give all very precise definitions. So, but well, you can catch me in some not precision. So that's well, nevertheless, well, they are defined just by a convex polygon on a plane, and the phase space of this this integrable system is a space of pairs. First is a curve such that it's given by a polynomial equation, and the Newton polygon is delta, and the first element of the pair is a line bundle on the compactification of this curve, a line bundle of degree g minus 1. So this space is contrary to the curve. The space of such pairs is a rational manifold. It can be parameterized, it's cluster right. But for a moment, I'm not going to use the cluster structure in it. So well, you have pairs of curve and line bundle. Of course, you can forget line bundle and you project in the space of curves. And the space of curves, well, essentially, well, space of curves is just a space of polynomials, roughly a space of polynomials of two variables with given Newton polygon. And this is just this map. It gives you the coefficients are Hamiltonians and Casimirs. So you have a collection of functions which commute with each other, but they are a little bit more than half a dimension because the Poisson structure is degenerate. Well, this is something. So there is a very large class of integrable systems which fits into this picture. Actually, the only two which it seems to me do not finite dimensional integral systems which do not fit into this picture or its limits. It's Hitchin integral system and Karol-Moser. And well, with Karol-Moser, maybe there is some relation to that, but well, maybe not about that. So I'll also recall some very basic facts, and I'm really going to speak about something very classical and classical algebraic geometry, so of 19th century. And well, I recall the relation between polygons and curves. So if, well, forget for a moment the line bundle, so let's consider a polynomial with the given Newton polygon. And it means that this is the sum such that the, of course, there is another condition which you should add, that Cij is not equal to 0, is if Ij is in a corner, Ij is in a corner is a corner or vertex of delta. All others can vanish. And well, this space is there is a basis of holomorphic differentials which can be written explicitly. So for any point inside the polygon, you get a you can write down a form which is holomorphic and well, given by the explicit formula using residues. And it's very easy to prove that this is holomorphic. And I will say one word why, but somehow there is a canonical basis of holomorphic differentials. However, what I realized just preparing this talk that Goncharov-Kenyon construction originally gives another thing, which gives the basis in the space of homology of the curve. This is kind of quite remarkable. Well, it's maybe I'll speak about it a little bit later. Now, so we have a basis. Therefore, well, this implies, for example, that the genus of the curve is just a number of points inside the polygon, which is also a result of more than 100 years old. Now the sides of the polygon correspond to points at infinity. So compactify your curve. Then, in order to get compact curve, you need to add points at infinity. And if you have a side of length m, so it means that, well, a side of the polygon can be a side of the polygon. One can illustrate a vector, which is just a vector. Well, you have a polygon, and every side is given by a vector which is oriented counterclockwise with respect to the polygon, and this is the side, and if the integral length of the curve, which is greatest common divisor of a and b, means that there are exactly you need to add exactly this number of points to the curve to compactify it, and for if you divide by m, then the order, well, the functions mu and lambda, they are functions defined on the curve C, but of course they are not, they have some poles or zeros at the curve C bar. So actually this vector is, well, divided by common divisor is more or less the same thing as just the order of the pole of zero of lambda and mu at this point. So,
just not being confused. So AB is the side in the sense that it's the end of the arrow where it starts from zero, yeah, or what?
Yeah. It's just a vector. It's here, yeah. The vector in the sense
move it to zero. Okay.
Of high school. Yeah. So two numbers. This arrow. So this is A. This is B. Or other way around. This is A and this is B. Vertical is B and horizontal is A. And so the A over M is just the order of the function mu, and B over M is the order of the function lambda in the points, all the same points which are you add. So all these points, they are kind of very similar to each other. So, well, what I formulate is kind of maybe complicated to remember, but it's very natural statement. And the reason for that is the following, that everything you do with this curve given by polygon can be, well, you can simplify your problem by using some degree of freedom. Namely, it's obviously that if you have a polynomial, then the curve doesn't change if you apply automorphisms of C star squared. So what you can do, you can, first of all, you can, of course, multiply all your coordinates by numbers, and you can multiply the polynomial by numbers. And you can also multiply the polynomial by not only by number, but by the monomial, because it doesn't vanish on C star squared. And you can just make this monomial transformation. by a matrix which is determinant one, inversible matrix. So well, on the level of polygon, it means that you can act actually action of well, this transformation is just action of SO2 semi-direct with Z2. So you can take do with the plane is anything you want. So you can apply SO2 and shift, and that gives the same curve. So using this degree of freedom, you can just given a site, for example, this one, you can move it and put it on well, you can always consider the polynomial. Well, you can rotate it in such a way that the polygon becomes well, one side is horizontal, so it's the point 0, 0 is the point 0 k0, and if you consider this this polygon, so the polynomial can be written in such a way. So it's just will be polynomial in mu, and well, if mu is 0, this line, well, the line mu is 0 doesn't belong to C star squared. So the points corresponding to mu equals 0 are actually points at infinity, and these points at infinity are just roots of P0. So therefore, the points at infinity are actually roots of the polynomial P0. So other things that if you have other, well, in other words, if you have a polygon, and here you have the coefficients A0, etc., AN, so the points at infinity, so there are, well, or complexification points, just use this term, is just the same thing as the roots of the polynomial A0 plus A1 x plus, well, mu plus etc. plus a n x to the n equals 0. So this is just a f of k. Better to write k because it's k. So these are just roots of this polynomial, and well, it's tentative to say that the points on the boundary correspond to points at infinity, but it's not really a bijective correspondence. It's because it's, well, it seems to me that it's not a bug but a feature, but nevertheless it's makes some problem. But nevertheless, the number of points at infinity is just equals to the number of boundary points. For example, the same thing, how to prove, for example, the fact that this residue is a homomorphic form. So it's obviously homomorphic in the finite domain, but you need to check that it's homomorphic at infinity. And well, you just check it explicitly for the case, and your polynomial has this form that it's homomorphic then mu equals 0, and well, it's really one line proof. So well, all the computations actually can be reduced. Many computations can be reduced to a very simple form because we can turn around this curve. Well, now what is the group of discrete flows? So the group of discrete flows is just the space of well, some transformation of our phase space, which I recall that phase space is the space of curves plus line bundle on it. And well, I do not claim, well, I will discuss a little bit how it can be extended as a group, but for a moment I will describe this group in the, well, different ways, because it seems to me that it's kind of useful to give different description of the same group. So there are, the first description is the following. So this, let's consider we have a curve, and well, once again, we have endpoints at infinity, and let's consider the group of divisors supported at infinity. So it's a discrete group of rank n-1. So it's rank. It's a free group, free abelian group of rank of div 0 is n-1 because we have n points and the sum of coefficients must be 0. So you have n-1 rank of n-1. In this group, we have the set of principal divisors. And the principal divisors certainly contain the group of generated by two functions which are non-vanishing inside the curve and have no poles inside the curve on C. So the function lambda and function mu, both of course are principal because they are divisors of a function. And well, it's a just group of rank 2. So maybe it's better to say that well, just subgroup is definitely maybe there are for one particular curve, of course, one might have other principal divisors, but these two are always Over's principal. And so we can take a quotient of all divisors of degree 0 by principal divisors, and this will be our group. And this group, by construction, acts on the phase space. Why? Because we have our curve and the line bundle, and we can just add the divisor to the line bundle and get another line bundle. So this is an action which is quite natural. What is the most important about this group? That really, well, of course, you can add any divisor and get some group, but these divisors, it somehow doesn't depend on the curve. So, well, if you have, for example, you can have all the sides of your polygon have length 1, then it really doesn't depend on anything. So if you have, well, you have polygon, then some polygon with some integer points inside. So you should imagine that all the curve, irrespective of the coefficient, have the form, which is something like that. So we have handles correspond to integer points, and every side correspond to a point which escapes to infinity. So this is one should imagine the curve in this way, like well, some kind of fish. So this is every tentacle corresponds to the side if there is one tentacle per side. So therefore, if you change coefficients, the curve changes, but the tentacles are still in bijection with sides. So this group kind of canonical doesn't depend on the curve in a given family. If you have well, sides are not of length 1, then in principle, if you change coefficients, it might happen that well, you cannot say which, well, you cannot distinguish between the two tentacles going to the same direction. And in this case, well, you can define this group. Well, this group is defined up to, well, only if you fix the values of Casimir. So if you really fix the roots of your polynomial, and you don't change the coefficients of the polynomial, then of course this group is well defined. And
Volodya, excuse me, is that picture you are using, it's corresponding to amoeba interpretation of the curve?
Well, kind of. I just want to, of course, the amoeba of the curve look like the only difference is that here is the, well, you need to draw just well, amoeba of the curve has this form, more or less. But any curve, what I want to say that, well, it's just a way to imagine the curve. Any curve was given Newton polygon has a form that its points at infinity corresponds to the sides of the polygon, irrespectively of the form of the amoeba. Yes, and of course it's kind of, in order to imagine, it's better to imagine because it's yeah. Sorry.
I do not understand what you mean by does not depend on the curve, because it depends on the boundaries, as you say, right?
Well, I mean the following, that if you have an element of this group, so this group is kind of, if you change the coefficients of the curve, then you can, well, this neither numerator nor denominator, they do not depend on the coefficients.
I see. So you mean internal coefficients, yeah? Because these corners might be non-zero.
Well, the corners are non-zero, yeah.
So you can also change them except for putting to zero. I see.
Yeah. You change fixing. One fixes the delta, and then you change all coefficients except the corner coefficients. Well, maybe you may even change corner coefficients, but keep them non-zero. So you fix the Newton polygon, and while you have this, you can enumerate the set of points at infinity by something, because if you well, for example, if you change the coefficients, you may have a path, for example, on, if you allow yourself to change coefficient on the boundary, it might happen that these two roots to points at infinity interchange, and so you do not, well, the group is changed by automorphism. You can fix the generators of this group, so to say. It means that, well, it doesn't depend on the coefficients. Means that you know the generator. You can identify it with z to the n-1 canonically. Yeah, so this is just this group. So then there is another description of the same group, and the description is quite simple. So you take your polygon, and your polygon is actually a matrix. You can associate a matrix of the size n times 2. So it means that just every side is a vector of size 2. So you take all the sides. Well, however, you need to divide the side by, so you have a side of length m. So you imagine this as a collection of sides of length 1. So you have some sides, so you make a matrix of it of size m times 2, and so you have a matrix. So you have a1, b1, etc., an, bn, and the sum of a's and sum of b's is obviously 0 because the polygon is closed. So the image of this matrix belongs to z to the n-1, and you take the z n-1 question. You take a quotient with respect to the image of this matrix, and this gives you the group. So it's also a very simple group. It's sometimes, well, its rank of G is rank of G is of G. Sorry. G equals to n minus 3, because the rank of this group is 2, so you have n minus 3. But you may have torsion, and it's usually you have torsion. G is the space of, well, another alternative description of the same group is the following. So you have, I'll use it a little bit later. So you have, you can associate to it a function, which is just you have some integers, a1, alpha 1, alpha 2, etc., alpha n. So you associate the functions, integer valued function on the the vertices, and then you take a quotient by quotient by the linear function. So you take all the functions on the vertices quotiented by functions which can be extended to a linear function on the whole plane, or affine function. So this is another point of view from the same group, and well, it's really something which is kind of elementary exercise to see this. This is a same thing. Well, so the discrete flows, which we describe this group G, is there are plenty of examples where it's really a discrete flow free integrable system. The example, the most popular one, sorry, that's something wrong here. There is no lambda. The most popular discrete flow is the following. So if you have a matrix, which is, well, not necessarily, well, here I speak about affine matrix, but it also can be affine dimensional. So you take a matrix in the space of the group GLN hat, and you quotient it by the constant diagonal matrices. Then on the space there is a flow which is just this matrix, any matrix can be represented as a product of lower triangular and upper triangular in the sense of affine group. So lower triangular depends on lambda inverse, upper triangular of lambda plus. In a fine sense. So this means that it's the sum of matrix depending on lambda inverse, and it's always triangular, then lambda equals 0. Lambda equals infinity, sorry, infinity. And here, other way around. So it's upper triangular for lambda equals 0, and it depends only on lambda, not inverse. So these two matrices can be inverted and write it down in the opposite order, and this is gives a automorphism of the space of matrices depending on lambda and lambda inverse. And this automorphism is a particular case of the action of the group. So, well, there are plenty of others, but what I want to concentrate myself, and I will just it's some example which is actually existed much earlier than all science about integrable system existed. It's just Penlevy parism, and I found out that it was published exactly 200 years ago in 1822. So it's worth mentioning even for this reason. So what's a Penlevy parism? And what I'm going to say that it can be really approach of Penlevy, so to say, can be generalized to all other elements of the group, and what I'm going to do. So what is Penlevy parism? So you have two conics, and the claim is the following. So if you start from one point here, for example, and you trace a tangent to the, you take a point on Q1, then take tangent to the Q2, you continue until the intersection of Q1, and then you repeat this procedure, and then you get a sequence of points of Q1 and sequence of points of Q2. So sequence of chords. And the theorem by Penlevy, which is 200 years old, so this claims that either you close every trajectory independent on the starting point closes after n iterations, or neither of them closes an iteration. So there are two possibilities.
Volodya, may I interrupt you? Am I mistaken?
Of course.
It's not Penlevy, it's Poncelet.
Absolutely.
Poncelet, sorry.
And
sorry.
Penlevy is just 100 years old, yeah.
Yeah. Sorry.
But
It's
that was the way for you to make it as much as possible close to the main topic of the conference.
Yeah, exactly.
Poncela,
of
he
course.
did it being
It's correctly written in the abstract. In the abstract on our webpage, I just checked.
Yeah.
It's written correct.
Yeah. It's correct. Yeah. Sorry, I was written. Well, yeah. It just I wrote it after listening to the talks of the conference, so it was Thank you, Poncela. So this is well, I hope you definitely know this picture. So how one can interpret that is as a in the setting of discrete flows of nature of Kenyon integrable system. So it's a kind of Gonchar Kenyon Poncela or other. So what is that? So you have well, one can consider the curve, and the curve is the space of pairs of points such that one belongs to Q1, one belongs to Q2. So Q is a projective space. So Q1 and Q2. So it's the curve belongs to just P1 cross P1. And I consider the pairs of points such that the segment is tangent to Q2. And well, and on the space of these segments, there is two involutions. First involution just keeps Q1 and changes Q2. And another one is changes Q2, keeps Q2 and changes Q1. So there are the two involutions. And well, I claim that C is actually an elliptic curve. And to do that, well, it's good exercise for students doing projective geometry. Namely, well, it's easier to do if you just consider, well, here I prefer to draw the curves where conics do not intersect. But to choose coordinates, it's better to draw conics as intersecting. And you have two conics, so conic intersects in 4 points in general. Let's draw two tangents tangents to both conics, common tangent to both points, whatever. Well, it doesn't matter which ones. We choose which one, and the third line will connect the two tangency points of one conic. And well, 3 lines defines you projective coordinates on the projective plane. So you just have 3 coordinates x, y, z, and here is y equals 0, is x equals 0, and z equals 0. And then you can also parameterize your conic, fixing the value of the parameter of the conic. So here the parameter is equal to 0, here is infinity, and the other parameter is also here 0, here is infinity. And you can write down the corresponding equation. It's also, I do not go into details. It's just some determinant. The tangency condition means that the coordinates of this point, and the derivative of this at this point, they are linearly dependent. So some certain determinant is 0. You can write down explicitly the equation, and the equation turns out to be this one. And it shows that, well, why I did some work to write this equation in this form, because I wanted really to show that the corresponding Newton polygon is a quadrilateral. Because if you take arbitrary coordinates, then in general you have something which is larger, but there are dependencies between coefficients. So this kind of here you just clearly get something to parameter families of curves, which correspond to two parameters of pairs of conics. So every conic have 5 parameters, altogether 10. Then you subtract the projective group, you get 2. 10 minus 8. So you have two-parameter family of pairs of conics, and you have two-parameter families of curves. And you can write down explicitly easily the change of the coordinates. You just take one involution preserves lambda and changes mu, another involution preserves mu and changes lambda, and you get this equation, which are actually one form of the equation, which was, the composition of these two is our evolution, and we've seen, it's a little bit slightly different coordinates in the talk of Professor Yamana. So in the lambda mu plane, the trajectory is very simple. So this is some realistic elliptic curve, and some real elliptic curve for some choose of B and C, and the map is just takes point on the curve, and this involution sends it to this point of the curve, then involution is just taking the points of the same vertical line, another involution takes the points of the same horizontal line, and this is just our discrete flow corresponds to the sending these points to that point. And why this is involution, and why this is the combination of that is actually adding divisors and infinity. The reason is very simple, because if you consider, for example, this point, I don't know, I'll call it U1, and this point is U2, and you point U3, then U1 plus U2, class of U1 plus U2 is equal to the is equal to the zero. It's and here I don't know, I'll call this V. So it's zeros of lambda minus V, and the divisors of lambda minus V, and the divisor of lambda minus V is, so therefore U1 plus U2 minus Z minus V, the divisors. I mean, the bracket means that the divisor of function lambda minus V is supported at infinity, belongs to div 0. So the U1 is, and this is a principal divisor. So in the group of modular principal divisors, U1 is equal to something, U1, U2 is some divisor belonging to A minus U1, where A belongs to div 0. And the same thing of U3, for the same reason, U3 minus U3 equals B minus U2. B belongs to div 0. So therefore you have that your evolution is just adding U1, U3 equals B minus A plus U1. And you add the divisors of the bits. So this is very, very elementary computation. Now, what I say, it's maybe not 200 years ago, clear 200 years ago, but maybe hundreds. It was already known. I will say, dare to contribute something which maybe, at least I didn't see it before. So the question is how to generalize this picture for higher genus. So if you have a curve which is not of degree, it's not elliptic, but some higher genus, or elliptic with more points at infinity, which correspond to some more complicated polygon. So how one can do that? And the algorithm is the following. So first of all, the idea is that, well, once again, if you have a polygon which is a little more complicated than a quadrilateral, then you expect to have a group which is of higher rank. So you have more involutions. And the so how to construct this this picture, and for sorry, more involutions, maybe if I can add, sorry, if I can, no, it doesn't work. Maybe no, that's okay. It's just copied my plane. Okay, so I want to construct an involution which is generalizing that. First of all, the phase space, just remark, if you fix, well, for simplicity, I fix the value of Casimir, so we consider the phase space, which is just the space of pairs of, well, I can identify the phase space with the space of pairs curve, and well, before I had the line bundle L, but now I identify the space of line bundles with divisors of degree G. And well, of course, this identification is not canonical because L is a line bundle of degree G-1, and this is the divisor of degree G. Well, I fix one isomorphism between, well, once again, I have some points, so I can, in principle, fix an isomorphism. And actually, this isomorphism will be unique up to the action of this group G. So this is not canonical, but almost. So what is divisor of degree G is just a collection of G points. Well, it's just belonged to C star squared. This is an isomorphism. Well, this is also a classical thing, which is called separation of variables. And it claims that if you have, well, it's a very simple statement somehow, well, what's trivial to verify that it's actually preserved Poisson structure, but well, and I don't know actually the simple proof of this fact. But nevertheless, the idea is the following, that if you have a curve, you have G points on the plane, so it's C star squared. You have G points, then, and you fix Casimir, so you have your Newton polygon. You have the coefficients here, C1, C2, etc., Cn. Well, and the number of points is equal to, here the number of points is equal to G. So it's, so you have exactly inside of that, you have exactly G coefficients, which you can vary, and you can trace exactly one curve. Well, for generic points, you can trace exactly one curve which passes for given G points. So you have an isomorph. You can represent your curve as your phase space is just a collection of G tuples of points. Of course, this really, well, this correspondence between phase space and collection of points depends on the polygon which consider. So this is important. So how to define an involution on this space. And the idea is the following, that the involutions are now enumerated by pairs of edges. So for any now a pair of edges of your polygon will define an involution. So the how to define this involution is the following. So you take two pairs, well, for example, on this polygon, you take these two pairs and you consider you take the Casimirs of, well, of course, these two pairs divide my polygon into parts. And well, the pairs are not in two parts. And then you take
well, just to be clear, What involution are you talking about? It's involution of the spectral curve or involution of the phase space?
Involution of the well, of the phase space, and involution, yeah, involution of the phase space, and this involution. Well, you have involution which preserves
the result of involution. It's changing the spectral curve. Am I correct?
No, the involution doesn't change the spectral curve. It changes the line bundle.
But not any curve has involution. Oh,
no. It doesn't change the curve.
Oh.
It doesn't change the curve. It's just my so you have your space of curves, and over every curve you have your Jacobian or Picard. And this involution is just acts on this Picard. And so like here, for example, I will use this involution to produce my discrete flow. So composition of two involution is just a shift on the line bundle. So the curve preserves, the curve is the same, but the points on it change. So what I want to say, well, what I want to do is I am going to do the following. I take a curve with G points on it, and I get the same curve, but with another G points. So I have G points here, and I change to another set of G points. And such that, so I have the points, I don't know, A1, A2, A3. So I take A1, maybe I should erase, sorry, I erase this curve. So I have the involution, something takes A1, A2, A3. And here you have B1, B2, B3. For example, if the curve is of genus 3, and I want that the sum of A B1 plus B2 plus B3 plus A1 in the Jacobian plus A1 plus A2 plus A3 belongs to the divisors with this supported infinity. Well, of course, it's not divisor of degree 0 because the sum is of degree 6, and this gives me involution on the space of divisors. And then composing these involutions, I get my group. So what is the idea? So you have G points, and you need to produce another G points. And how you do that? So you have a curve, yeah, and then you just change the naive idea is the following. So if you have two curves with the same, maybe I should, well, I have no much space to draw. Maybe I'll do the same page. So I'll, it's a little bit mess, but I draw on here. So you have a curve which corresponds to the Newton polygon delta, and let's consider another curve which corresponds to the same polynomial, but not just another curve. So it intersects the original curve in some number of points. And the number of intersection points, so both curves correspond to the polygon delta. And the number of intersection points, I claim that the number of intersection points, which is written here, is equal to this number. So it's 2g plus n minus 2. So it's a number of intersection points of two curves with the same Newton polygon and generic otherwise. And this formula is just, well, it's a consequence of two formulas. First formula is Bernstein Kushnirenko-Khovansky, which tells that the number of intersection points is mixed volume of two Newton polygons, but in this particular case, two polygons coincide, so it's just a volume of the twice the volume of twice the area of the polygon. So, and on the other hand, the area of polygon is computed by plus peak formula, which, well, then you can compute the number of intersection points, and you have 2G plus n minus 2 points. So the idea is the following. So you take you have these 3 points. Then you trace a curve, which is, well, maybe it's, you have these points. I'll take them. You trace a curve which passes through these points, but with other values of Casimirs. So instead of writing the Casimirs ABCD, you just shift this coefficient, you just multiply by any constant. Actually, the result doesn't depend on this constant. And for example, you may multiply it even by 0. Of course, the polygon changes, but well, it's the same thing. So you trace the curve, and the claim is the following. So if you just take the arbitrary, you take arbitrary Casimirs, then the number of intersection points is equal to 2G plus n minus 2. But if the Casimirs are like I prescribed here, so you have you keep Casimirs on one side, you keep the same, well, unchanged, and on the other side you multiply by a constant. So the only points at infinity which move are the points corresponding to the red sides. So in fact, the old curve and the new curve intersect at infinity on all sides but 2. And so of course, the number of intersection points is 2G plus n minus 2, but n minus 2 of them are at infinity. It's just a way to choose the, well, to push all the points except n minus 2 points of intersection at infinity. And in fact, the curves intersect in exactly 2G points. So the algorithm is the following: given this curve, so I choose some zeta, and I trace a curve. Well, I have one curve, then I change these 2 Casimirs, and I then trace another curve. Maybe I should draw on this picture. I have these points. I trace another curve. Well, I trace another curve. It intersects at 2G points. So I have, instead of these 4 points, I have these 4 points. And it allows me from one photoball of points to obtain another photoball of points. Well, once again, I just explained that this is one can take psi equals to any number, for example, 0. For example, well, I'll maybe double the picture to be able to draw. So, for example, suppose you have a polygon which is just standard polygon of this one. So, if you, for example, multiply. If you have a Casimirs A, B, C, D, well, and you multiply it by zeta, and zeta equals, you tend zeta to 0. So one curve will be just your curve, and another curve will be, the only non-zero coefficients will be this one and this one. So it will be something like a lambda plus a constant plus a constant. So, and this is just vertical line. So this is a lambda plus c equals 0, and this line is b lambda plus b mu plus z equals 0. So if you just choose the 2 edges like that, and multiply all this like size, so you get your curve is well, second curve is just a line. So it's generalizes the construction of this picture. So you just really produce two other well, out of one point you produce another point by intersecting it with the line. And the same thing for well, here you well, in this particular case, and which is Poncelet, this is just, you can cut this angle or you can cut this angle, and well, you get, for every angle you get involution, the composition of them is exactly this picture. So the claim is the following, that you can do the same picture for the same procedure for any curve, and this is purely geometric, and you can write down explicitly the involution of the space of G-tuple of points. And of course, this involution depends on the values of Casimir's. So but this will be a map from divisor of degree G to divisor of degree G, which just reproduces this picture. And the claim, well, the theorem is that in this way you can obtain any divisor, which is any element of your group G. So the claim is that well, somehow you can obtain this group in this purely geometric way. Another theorem which I well, want to say, that this group G actually is realizable as a sequence of mutations, So it's definitely contained in the mapping class group. However, it's clear that there are some other transformations which do not well, claim. So G is realizable as by sequence of as mapping class group cluster mapping class group. There are other transformations, and in particular, if the sides of the polygon are not of length 1, there is some non-abelian part of this. Well, it's always virtually, well, the mapping class group, so far, all the known examples are virtually abelian, so it's abelian up to finite group. Always has finite index abelian subgroup, but well, for example, this well, there are this affine Weil groups which appear, but kind of well, they always contains this group G, which I described here, and well. Well, there is also kind of explicit construction of this group as a sequence of mutation, but maybe I'm not going to speak about that. It's also, well, essentially it's contained in our paper with Andrei Bashakov, so there is, this construction is really quite old. Thank you very much, and I stop here.
Thank you. So please, questions?
So I wanted to ask about the definition of this reflection. Does it depend in any way on this second curve or not?
Depend on
the second curve with the same Newton polygon.
No, it doesn't depend on the second curve. It depends. No, it doesn't. Well, you have actually, if you have change a sorry. If you consider well, you have one polygon corresponding to the P, have P1, which corresponds to the this polygon, and here you have P1, for example, and here you have P2, and you consider the curve passing through G points corresponding to those Casimirs, and P2 corresponding to these Casimirs. And of course, if you consider any linear combination of them, P1 plus lambda P2, lambda, well, in lambda it's not lambda, alpha P1 plus beta P2, all those curves pass through these G points, but they pass through all these two G points. So you have just a how to say sheaf of curves which passing through two G points. So in particular, well, it doesn't depend on which constant you choose here, because you can always choose the constant such a way that this two numbers coefficients become 0, or these three become 0. It doesn't matter. So you just change. Well, you actually what you do, you just consider a sheaf of curves passing from the G points, and this sheaf has actually two G basic points. So you take this G points, you throw them away and keep the rest. If it's okay, clear whatever.
Yeah, thank you. So
Volodya, maybe it's unrelated, but the picture you described sounds very similar to what in old days Moser and Veselov took as a definition of completely integrable discrete systems. Namely, you take an operator depending on lambda, say of order 2, degree 2 in lambda. You split it into factors, and that corresponds to the choice of specific points at the infinity. Then you just exchange these factors. This is conjugation. That doesn't change the spectral curve, but makes a shift on the Jacobi. And somehow their claim was that all completely integrable discrete systems are of that nature. Do you see any relation of this?
Right. You mean this? Well, what is? I try to draw somewhere here. Well, this transformation. You mean you take the product of A plus A.
Yes, you factorize and somehow
you factorize and then you rewrite in inverse order.
Yes.
Yes, exactly.
Okay.
This corresponds to the following situation: that if you have a polygon, so you have its leftmost part and rightmost part, and you may you fix the edges, which are one is just this one and one is this one, and so this particular choice of the edges, if you consider this evolution corresponds to this one, more or less there is one particular transformation of the polygon which corresponds to this transformation, particular element of this group which corresponds to this transformation. But it depends on how you look at this polygon. If you look
I'm
at
saying the factorization is not unique, so there are different commuting as a result of laws. I just want to recall also a remarkable understanding what is discrete integrable system is from this point of view, because typically when you start doing some kind of discrete iteration, the number of points you get in the image is growing exponentially. Completely integrable discrete system, when this number of images grows polynomially. And that is somehow summary of what.
You speak about the number of points.
I'm speaking about any correspondence which naturally appears in discrete dynamics. You have a point, and actually in discrete dynamics, the image is not one point. It's say a couple of them. Just two ways how you look on the tangent of your billiard. So you have two images at the beginning as the first iteration. Then you iterate, you get 4 points. You can keep going along your discrete flow, and it gives you usually exponential growth of images.
I see. You mean just if you have something which, well, you have two transformations which do not commute, for example, you get, of course, exponential.
For example, you have a correspondence, you have a curve, you just reflect one coordinate, but you can reflect two, so you have two images. Then you iterate. If it's something non-integrable, you will get that after n iteration, the number of images would be 2 to the power g, 2 to the power n. But if the system is integrable, then the number of points grows polynomially. And that was the characteristics of integrable discrete floors. Analog of Liouville theorem. Okay.
Yeah.
Sorry.
Yeah. Of course, this is well. Here is integrable in the sense that there are this Liouville. It's really in the Liouville sense.
No, it's Liouville because it grows not drastically because it shifts on the Jacobian commute. So that is the reason of cancellation.
What is really a question which I try to figure out is what is the number of fixed points of this evolution, and well, how it grows with, and this, well, so far I have some vague idea how to compute that, but really not so many. Fix well, how to consider what was the structure of the point such that in the space of curves, such that their certain iteration is for finite order.
And what is the conjecture for the answer?
Well, the conjecture for the answer that these curves correspond to the spectrum of well, some. I would better not to say because it's a little bit too fantastic, but I don't know. I'll draw the picture and then we can say.
So, Pasha, more questions?
That is related to previous talk.
I see. Then Pash, more questions? Then maybe some short, or I don't know.
Yes, so I wanted to ask, what are the relations specified by all these reflections corresponding to different sides of the Newton polygon, or maybe what happens if we consider all possible reflections of this kind?
Well, you consider this still this group G, so you have this polygon, and sorry, how to say that? So if you maybe sorry, I will go down. So what you get as a divisor. So you have here, well, actually you have here some depending on well, but you have here you have one, and here you have one as well. So it means that, and zero everywhere. So sides correspond to sorry, 1 minus minus 1. Sorry, 1 1. Yeah, I did correctly. So what I want to say that this sum it's, so you have G points and, oh, no. excuse me, I just trying to formulate correctly. I want to say the following: that is the divisor, which you with respect to which you reflect, is supported on these two sides. So these sides correspond to points at infinity. So you have all these points at infinity correspond to sides. So the question is, what is what is the divisor? Well, the elements of my group are actually some divisor of degree 0 at infinity. And I claim that there is a simple rule. Perhaps I should have written it, but well, I'm afraid to be messed up. This you can explicitly write down the divisor which correspond to this this composition of two involutions. And the first is kind of reflection of the divisor, which is supported on these two sides. And if you take another involution, so it will be supported to other sides.
So that after group everything generated by these reflections is just some translation group plus inversion. Yes.
Yeah. So it's this is just a group which is a composition of two even number of translations is just the same group which we had before. So this is it's a just geometric way of obtaining elements of this group.
Probably I want to ask another question. If you have several integer points on a side, I don't know any generalization of this construction which can give some permutation in groups, which can be combined.
The answer is very good question. No, I don't know. There is this guy Tsukasa, I don't know if you know him, who is working on this subject, but and he claims that he knows something about that, but I don't know. He writes very long texts, and I couldn't yet manage to figure him out. But this question, he even. You may. If I'm correct, it's Tsukasa.
Ishibashi. Yeah.
Ishibashi, yeah, exactly. This I remember well. He's a very kind person, but he writes complicated texts.
Thank you.
Okay, so let's thank Volodya again and see. We just have 2 minutes.